Programming Challenge Part 1. Okay, this is where we left it with the last video session. We covered seal-in logic, and then we covered latch-unlatch logic with a semi-practical application with a conveyor. So if you see here, we have a start-stop circuit or logic for an electric motor. I mean, it's for a bit memory, but it's affecting the operation of electric motor. And then we have some logic to declare a size fault if the carton is too long. From here we're going to continue with the conveyor, but much more complicated. And this next lab project involves 3 conveyors. Now we'll keep building on this, so this is just Challenge 1 Part 1. We're just getting started with this. But it will extend from that previous conveyor lab, and I give you a functional specification. 3 belt conveyors, each with a motor driving the belt, which means that you need to control 3 electric motors, and each one drives a conveyor that you see here. So you got motor 1, motor 2, and motor 3. We want a start and a stop push button for each conveyor. So you have to be able to manually start and stop each conveyor individually. Not one start button starts it all and one stop stops it all. So each conveyor needs its own logic to control the motor with a start-stop logic. With an interruption in program execution or power, we do not want the conveyors to continue running if we leave the run mode and return to the run mode. Now we did that, we kind of demonstrated how you could do that before. Between seal-in and latch-unlatch, you know which one will drop out the bit. But nonetheless, if the controller leaves the run mode, whether it's because you went to the program mode or because you cycled power, we don't want anything to come back up running. We also want a system start and a system stop logic to enable the conveyors to run. Enable only, not to run them, or disables them from running. This does not actually start and stop the conveyors directly. Just enables or disables the ability to start the conveyors. In other words, if regardless of what's running, if you hit the system stop, it stops everything. If you hit the system start, it doesn't run anything, but it enables you to run those conveyors. Each conveyor will have a unique runner logic to start and stop them. If the system is enabled, that kind of blends in with number 2 in the functional specification. I say do not turn the page unless you want to see the solution that we are providing before you've exhausted your own imagination. So depending on the circumstances, this learning collateral and your location, if you're in a live classroom, you don't have all day to do this. So if you want to take a stab at it real quickly, please do so. Otherwise, you should turn the page and go with the solution that we show. You may want to delete your existing logic and symbols before starting. We will not integrate the full electric eyes until much later in this manual. So right now you just need start-stop for the 3 conveyors and a system start-stop. Now depending on whether or not you have switches wired to an input module, again, if you're in a live classroom, then you are probably using our universal digital field device simulator, which has 6 lights and 6 switches. We also are introducing or have introduced a term, module defined data types. Those are the data structures that you get automatically with I/O, meaning if you add an I/O card, it automatically adds a data type into your memory. Now in the MicroLogic's SLC 500 realm, they just I words and O words. There's nothing really beyond that. But when we get to a newer platform, if you take the 5000 class, you will see that module-defined data types become much more important. Either way, it refers to memory locations that are automatically designated when you add I/O modules to your hardware configuration. And again, I want to emphasize it's extremely important that you take this opportunity to exercise your imagination by applying what you've learned so far. Now, if you're listening to this video after the fact, we're still going to go over, starting right now, our solution to this challenge. Now remember, I told you that you could delete all of your logic. You could create a new project, but remember, if you create a new project, you have to be careful what you're doing with channel configuration. You know, channel 0, we're using 38.4K for our RS-232-DF1. And for channel 1, you have a specific IP address for your station. If you're using the Micrologix 1400 stations in a live class, then your controller should be 100, 100, 100, and then your station number, 221 through 230. This particular one I'm using right here happens to be 226. If you create a new project, then this whole pop-up here is going to be boot P enabled, and this is all grayed out. And when you try to run your processor with Ethernet, it's going to be looking for a boot P server out there, which we don't have. Once you have your channels all configured, it's probably a good idea just to delete the logic. As a matter of fact, I'll do that. So I just highlighted one rung, put the focus on rung 0, header, delete, 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 got rid of them all. Now I'm going to go to Tools, and I'm going to go to Database, and I'm going to delete the database. Okay, that will delete all of the symbols and descriptions that we have used so far. However, I'm going to save this. I'm going to save as, because I don't want to overwrite the program that I was using. So I think I will challenge 1, part 1, page 86. So we could have used some of the logic from the previous lab, but I'm going to add it in as I go. But I'm not going to make you watch me. I'm going to pause and then come back. While I was paused, I put in one rung of logic, and I swapped the start-stop around just to emphasize it doesn't matter what order you put them in, because these two conditions are in series. If you hit the start button and the stop button's true, which it isn't right now because I don't have B3 0/1 on. Notice that I'm using all B3 bits because you can create your logic and test it with any bits in your logic. There's just a whole bunch of things that we're going to do that this works out well with, including simulated start-stop push buttons in a situation where we don't have enough actual hardwired I/O to do everything that we want to do, so we need to use internal bits. This is our first rung. Now that's our stop push button. Remember, that would be like a normally closed. Now in this case, I could use a true of off and leave that off to make it look like a hardwired electrical circuit, but I want to stick to the logic. If I toggle this bit on, it goes on, turns on the motor, or the bit that represents the motor, but I have to toggle this back off. Later on, I'll show you a way to get around that. Remember, we have 3 conveyors, so we need 3 circuits like this. Just to show you a little shortcut, I'm going to select that, and I'm going to hit Control-C, Control-V twice. If I didn't want the rungs to pop up there, I could have put the focus here and put Control-V twice and left this one alone at the top. I'm in the process of adding 2 more start-stop circuits, but I thought I would show you some of the ways that I kind of save time. So I'm going to go up here, right-click there, Edit Symbol, Control-C to copy it, click off of it, don't change it, then go down here, and I want this to be bit 3, and of course you notice that no symbol comes up. I can't just copy and paste that in there, but I changed the 1 to a 2, and then I've got it. Same thing down here. So this would be 3, 4, 5. So change that to bit 5. Double click again, Control V, change that to a 3. Okay, see, I've cheated there. Now I'm going to go over here real quick and double click there, Control C. Then this would be 1. Now that I've got a memory location, I can double click on that and paste in. Same thing here, make that a 2. I'll just paste it in right here and change it to 3. There you go. I think I may have also showed you that you can select more than one edit zone, and because I still have B310 for all of these, so I need to drag this down here, double click, drag this one down here, select the two edit zones. I didn't actually start all of these, but because I copy and pasted, I carried with me some states that we're on. So I'm going to toggle off all of these. It's a pain, you got to toggle them back on. So one toggle is one state change. So to truly toggle it, if you like the idea of a toggle being on off or off on, that's what you have to do. You have to toggle it to one state and then toggle it back. So here's our three motor controls for our conveyors. Now we need to add our system enable. So I'm just going to take and Control C, Control V, start editing this one. I'm going to use a completely different word in a B3 file. Use B32. Now I want you to notice something. Here, if I hit space, I don't get an underscore, I get a space. You got to use an underscore. Start system underscore push button. Now if I'll change this to word 2 bit 1. Now if I double click here and type in stop, now watch, I'm going to hit the space bar. See, I get an underscore. So if you're using the pop-up description symbol editor, you have to put in the underscore. But if you're just clicking on the address or the memory location that's already in there so you can enter a symbol, if you hit the space bar, it will put in an underscore because it knows that you can't use a space. The reason that does not work in the auto describe pop-up is because you could use spaces in the upper part of that. So they can't, for that particular pop-up, they can't divide between where you can use spaces and where you can't, and then put in underscores for you. So stop system, space bar, push button, enter. And this is going to be B330, which is yet another word. Now see, I can't, if I type it in here, it won't accept a space. I mean, it won't replace a space with an underscore. So I'm going to go out here, double click, and then type in system enabled. Drag this down to here. Well, this this is good because this is the kind of stuff that happens to you all the time. Okay, I did not expand the B3 file. That leaves me in a quandary here how to tidy this up. See, it says unable to create data table because I'm using word 2 and word 3 and 1 which do not exist. So I'm going to try and cheat. I can't finalize this, but I can select it and do a Control C and copy it. Okay, I saved it, went offline, but notice it did not save the system enabled rung that I had started. So what I'm going to do is go up here, because remember I copied it, Control V, and I've replaced it so that if you're offline and you put in an address that doesn't exist, it creates it for you. But I'm going to go here and see, now I've got 4 words. I'm going to go to properties and I'm going to make it 10. That way I know I'm not going to run out. So I'm going to go up to the timers. I've already got 10 there. Counters, I got 10. Control, we probably won't use much in the way of control words, but I'll throw in 10 anyway. Integers, we got 10, and floating point, we have 5. Okay, now I'm going to download, and I'm back in the run mode. Our logic has gotten a little big to be completely on the area of my screen that I have blocked out for this software. So I'm going to geezer down. These are the geezer buttons up here. Geezer up, geezer down. So there's a geezer down once. Now you can see all 4 rungs. We've got the 3 conveyors, and then we've got a system enable, but we have not integrated the system enable. So I'm going to put this rung into edit mode, put in a true if off, and drag that memory location down. Then I'm going to right click, copy, double click, Control V, double click, Control V. Now I'm going to select all of the edit zones. After you completed the logic, we had you put the system at rest. Well, after you downloaded your edits and went online in the remote run mode, I had you put the system at rest as shown in the illustration, the manual. And that means all of the stop push buttons are on, which they are here. And then the next step, I had you toggle all of the start buttons on and off, starting with B320, start system push button. Right click toggle, right click toggle. 2 toggles is the same as press and release. And it put it in this state. So we have 3 conveyors running, and of course the system is enabled, otherwise the conveyors would not be running. Then I had you toggle any one of them off the stop push button. So you press the stop push button and then release it. And the question was, did the conveyor stop? Yes, it did. Did it affect any of the other conveyors? No. Now, a lot of these questions are obvious, but the obvious questions are meant to emphasize and cement the obvious in your thinking. Toggle the stop system push button off, then back on. And you see the instant that I broke the logic here and dropped out the seal-in bit, then all these bits went false and turned off all the conveyors. Did any conveyors stop? Yes. How many conveyors stopped? I said all of them instead of 2, just in case you had restarted the one that you already stopped. Did any return to the on state when you toggle the stop push button on? Meaning, when we toggled this off, and the question is, when I did this, did any of them start back up again? Again, that's obvious, but we're emphasizing that. Toggle the start system push button on and off, this one. Did any of the conveyors return to the on state? No, they did not. Why? Because the seal-in logic dropped out. That's the whole intent of this type of logic, is that it seals itself in, but anything that breaks the true continuity through the rung, such as the system enabled going off, then drops out these 3, I guess you could say these 3 instructions do the false execution and turn those bits off, which effectively stops those 3 conveyor motors. Now in the next section, we're going to add logic to simulate a momentary start push button. Now the reason that we're doing this is because it's too easy to do this. This one you remember to turn off, but you forgot to turn off that one. Guess what? When you toggle that bit, comes right back on after you finish toggling the stop bit. That would be effectively holding down that push button while you push and release this. Well, of course the conveyor is going to start right back up. Rather than take a chance on you failing to do that, and by the way, in this code, I can click there and do the same thing as doing the stop push button, only I can do it with 1 click. So I can turn this back on right from there. Rather than toggle this on then off, or off then on, I can just toggle that. Okay, and effectively does the same thing. But we're trying to be realistic here and treat these like push buttons. Okay, now what we're going to do next is we're going to jump ahead and use some timers to create ladder logic diagrams that simulate someone operating the conveyor. And we're going to add this logic after the rungs that you're looking at right now. We do this only because we have not aliased our actual module-defined tag members with these tags, symbols. In other words, we're using internal bits in the binary 3 file, not using real I/O. I introduced the term here, module-defined tag members, and tags, parentheses, symbols, to introduce you to a concept that you're going to have to fully embrace when you get to the 5000, RSLogix 5000, that supports the processors that run the Logix engine. I had you save your project as Challenge 1 Part 2. You can name it anything you want. The smart thing to do, if you're going to take what you see right here, which if you look up here, I've got it Challenge 1.1. If I make edits and then I forget to save it as Challenge 1.2, instead I accidentally save the next stuff we're going to do that we're going to add, it overwrites Challenge 1.1. I'm going to save this. I'm going to go offline, and then I'm going to do a save as, and I just change the 1 to a 2. Furthermore, I'm going to put in, that's just a little extra help for me, and of course these page numbers get changed as I add stuff to the manual, but it gets me close. So now I'm going to add some more logic. Before we add the logic for the push button, consider this. If you were to describe the action of a push button, you would describe it as, if it's a normally open contact on the push button, the input that it's wired up to is off. When I push the button down, that input goes on. When I release it, it goes back off. The only thing that was left out there was the length of time that it was on. So to simulate that, we're going to use a timer to simulate that little bit of pause that you get when you push a button and then release it. Okay, I put in some logic. Before we put any nomenclature on it, or tag names, pointers, look at it. True if on. If a bit is on in memory, then enable the timer. Now looking to the right, you see EN and DN. Those are indicators. They aren't operators. You can't do anything with those graphics on the screen. They're just there to show you it's enabled or it's done. But we're not covering timers yet, so we're going to keep this pretty simple. We have no pointer for the timer. In other words, we're going to create a timer data type and we're going to give it a name. A timer data type is a class of objects, and once we put a name on it, like T4:0, then it becomes an instance of that class of data objects. And then in parallel with it, we have a true if on energize output. I'm going to add the memory locations for these instructions, and there's actually more than 4. Technically, there's a new rung, true if on, branch start, TON, then there's a next branch, true if on, energize output, and branch end. If I double click, see, they don't show the new rung, but it's there. XIC, no address. Branch start. So the branch start comes before the TON, but the way it's executed, the TON is executed first. Then we have this is, for the TON, this is the time base, the preset, and the accumulate, and you see there's nothing there. 1.0 is the time base, 0 is the preset, and 0 is the accum. Then there's next branch. Then we have a true if on, we have an OTE, and then a branch end. You could actually enter the values right now. I'm going to do this. This is a little off track, but I'm going to do this. So I'm going to punch in B3, and because we're using word 2, we have to use a little bit more information. Okay, you see what that did? So let's go back to our text here. We got a branch start and then a TON, and I'm going to do T40, and then I'm going to use 1/1000th of a second, and I'm going to have a preset of 200, and I'm going to leave the accumulate 0. Next branch XIC is going to be T4:0 dot TT, and then for my OTE memory location, I'm going to use B3 2/0. Hit enter and see everything's filled in. Now there's no nomenclature on the timer, and in the manual I had you do something, so I'm going to double click here and type in start system pulse. You notice I'm typing in lowercase, but it's showing up, and there I hit the space bar and got an underscore. So that's another place you can save a little time. SYS space PULSE. Now I hit space, but I got underscores. Important to notice. Okay, notice that the pointer that I put on this timer data type, start system pulse, also showed up with a /TT. Remember I told you that you can put a symbol on a word and then all the bits show up as that symbol slash and then that bit number. So I'm going to, I could right click here and do something, but I'll just click up there. I seldom ever right click and verify wrong. I almost always go up here and click. You can do it either way. So now we have a start push button, and you're probably thinking, well, B320, B320. What we got going on here? B320. So let's run this puppy. I'm going to have to geezer it down in order to get it all on there in our capture area. There's another way to do this, and that I'll geezer it back up, and that is to drag. You can remove some of these toolbars. So you see that I removed them by going to view, and I turned off some things, some toolbars. Now I can drag this down and get more in my view. So I've got everything in my view now. So I'm going to go comms, system comms, pick that controller, download. I'm going to toggle, it's still not a push button, but I'm going to toggle this button on. Now you saw it go on, but it went right back off. That's because this logic down here, consider when I toggle this, I'm also toggling this and this. I'm toggling the memory location that all of these instructions point to. So we have two instructions here that read the bit, and then we've got one right here that writes to it, correct? I'll geezer it down one more time just to make sure it's all on there and easy for you to see. Now I don't have the same thing done for the stop push button. So I'm going to toggle this off and then back on and then do this again. I mean, I could toggle it here. See, it goes on and right back off. So that saves you the extra toggle. Now I'm going to do the same thing for the off. In the manual I had some screen captures that caught the bits on. Now you saw them turn on the screen and then right back off, so you know that they went on. So I'm not going to belabor that. I explained that well in the book. Now it says, how many locations are there in the logic where the start system push button is used? Well, I would say 3, because you have 2 true-if-ons, then you have an energize output. If you said 2 because you weren't considering the OTE, then that was correct if you don't consider the OTE. So 2 or 3, but the correct answer, most correct, is 3. So now we're going to add logic to simulate the stop push button, which is going to be a little different. Okay, let's look and test our logic. You can see that the system is not enabled. If I toggle that bit, it goes on and right back off. This logic, when it sees that you toggled it on after 200 thousandths of a second, 2/10 of a second, the timer timing pulse goes off. So the timer timing pulse is on for 200 thousandths of a second. So when we toggle this bit on, and just to emphasize that, I'm going to bump this up to 1 second so you can watch it. So you see what happens when this is true. You toggle this on, starts the timer, it's enabled, and then this is the timer timing pulse. This pulse is true in between the accumulate being 0 and reaching the preset of 1000. So this is true for 1 second. So it turns on that bit for 1 second. But remember, last man wins. So we turned it on here, but there's no other OTE with that memory location on it. Remember, that's a push button. It's not an output. So we're not opposing other OTEs with that same memory location. So we're actually turning that bit on here, even though we turn it on here, I guess that sounds like double talk, so we turn it on here, and then this keeps it on for the length of the preset. I'll change that back to 200. The kicker here, or the crux of the biscuit, as they say, is that after 0.2 of a second, this is now false. This might still be true. This is true, but that's false. And when that's false, the true execution is not going to execute. It's going to be the false execution. So when this is true, this is true, this is true, this is on. When this goes false, then the false execution sets this to 0, so it turns it right back off. So that's why I call it start system pulse. So we're just creating a pulse, and the timer timing pulse keeps the bit on even after I've removed the toggle. Because remember, when I toggle this, it's instantaneous. When I click on that, it would go back off after one scan, except that this bit is being held on by that timer timing bit. Now let's look at the stop. That's a little harder to look at because we can't get the whole thing on the screen. But if we look up here first and I right click, toggle it once, it should go off and come right back on, leaving this system not enabled. If I go down and look at the logic, and there's many ways to do this. This is just one. Matter of fact, later on I might show you another one. Is the timer done right now? No, it's not. See, this done pulse or done bit is off, so this is false. But this bit was latched the last time the timer was done. It's because it's a latch, not an OTE, it stays on. And we want it to stay on because we want our stop push button up here to be on right now. The next rung here says, is the stop push button off? If it is off, in other words, if you toggle it off right now, right click on B321 and toggle it off, we'll just make this 2 seconds so you can see. Whether I toggle it off here or up at the first rung, it doesn't really make any difference. So I'm going to toggle it. And you see after 2 seconds, this was done. This was true, latched that bit, but this was now off, so this instruction is false. In other words, the timer data type is no longer enabled, and so it clears the cumulative value. The timer timing pulse holds that button off for whatever length of time. So let's do that again. I'm going to toggle this again and watch. See, this timer timing pulse is executing the unlatch. Remember, if the unlatch is executed, it turns the bit off. So when this is true, that bit memory is going to be off. That may be a little hard for you to look at right now, but if you keep playing with it, you'll see. As long as that's true, you're unlatching that bit. When this is false, and this is true at the end of the timing period for this timer, when this goes done, it sets that bit. This is false because you released the button, and then it holds it off for 2 seconds. So these two are exactly opposite. This one holds it on for 2 seconds, and this one holds it off for 2 seconds. That's why this logic is a little bit more complicated, is because you're holding it off instead of on. I'm going to bump this back to 200. Okay, this was the system start stop. Now I want you to, well, in the manual I had you add the exact same logic for 3 more sets of buttons, the start stop buttons for the conveyors. There is an easy way to do this, well, easier. That is, click there, then hold down the shift key and click there, and then right click, copy, then go down to your end statement, right click, paste. That puts one, or you could go Control V, Control V. Now I've got 3 pairs. There's one, and there's one that all need the memory locations changed for unique memory locations for each of the 3 conveyors. So I'm going to pause and make those edits. Okay, I made the edits for the logic. Down here, I added all of the simulated push buttons. I'm going through and I'm operating this, and in my haste, I made an error. I haven't went and looked yet to see what it is, but watch. When I toggle this bit on, it goes on for the 0.2 of a second, but the stop bit is not on, and it should be on. See, I can toggle it on and off this way, but it's not working automatically. So something is amiss with that logic. So we go down to the third set here, and I probably forgot to change a bit. Okay, let's see. Oh, right there. Having made all these mistakes many times, because when you're doing logic where you do, let's say, copy paste like I did, it's real easy to miss at least one memory location. So we'll look at one that's correct. I'm working, this is the off for conveyor 2. I'm using timer T45. You see T45 timer timing bit, T45 done. Now let's go down to this one. And what do you see? We're using T47 timer timing, oh, T41. I forgot to change that address. In other words, the logic is correct, but it doesn't point to the right memory location. Backspace 7. Now we go back up here, and I'm going to turn that conveyor on. It goes on, right? I'm going to turn it off. It goes off, but that bit comes right back on. That's what we want. Now these are still on. I'll stop the system, and you see they all drop out. When I start the system is enabled, but there's no conveyors running. So I can go start them one at a time. I don't have to have them all started. So you see, this is really a manual control system for these 3 conveyors. You manually turn them each on and off as you need them, but only if the system is enabled. So rather than have you hit 3 stop buttons to shut the system down, you only have to hit 1 stop push button, and anything that's running stops. Okay, I did have a question there in the manual. Compare the logic in rung 11 to that of rung 9. Are they identical? Well, they aren't, because what I did was I redid the stop conveyor pulse to show you another way to do it that looked much simpler. Might be more difficult to understand. So I'm going to edit my logic now to match that. But the answer was no, they didn't match. So if you look at these 2 right here, they match. So 9 and 11 match. But now I'm going to edit the logic. So we'll verify or accept if you like. And then we'll go up and try it. And that was for, oh, we do have to have the system enabled, and that was for conveyor 3. Okay, now we'll try the stop push button, and it works. So I would probably have you go back and change all of that logic so it matches. And just so we answer any questions that were in the manual, I had you go through and operate the logic. And then the last operation, toggle the stop push button once. It should like this after the toggle. The system stop. And of course that kills everything. Try toggling on any or all of the conveyor start push buttons. Did any of them energize the conveyor motors? Of course they didn't. No, is the answer. Did you see the push button flash on momentarily? I'm going to say yes, because at 0.2 of a second you should. Why do the conveyors toggle on or not? In other words, why are they doing what they're doing? And I would just say no, system enable. When you toggle the system stop push button in step F, did everything stop? Yes. And the why is it dropped out the seal in logic. You might have more wordy explanation if you like, as long as it means the same thing. How many push buttons are you simulating in this exercise? I'm saying 8, 2 for system enable and 2 for each of the conveyors. Okay, just for fun, we use 2 different approaches to simulating a normally closed momentary push button. In the resting or normal state, a normally closed push button is closed, completing the input circuitry for the field device. Hence, that bit is on in the controller's memory in the resting or normal state. And then in the manual, you see the goal of the logic is to momentarily interrupt the resting state. Just like if you were energizing a relay and then de-energizing, you momentarily interrupt the state of the bits. And I gave you a step-by-step explanation of that logic. Okay, save your project, and I'll see you in the next video.